Alrighty then. Yeah, John Suykerbuyk joined this group about 2 or 3 months ago and just been having a fantastic time ever since. So, and it's funny that we're talking about tape again and stuff like that because I actually started in the storage business, golly, 15 years ago in tape, and I've done hard drive firmware, done some SSD stuff. And anyway, now we're full circle back again. But there's been something that's been really itching at me that I just want to share with the room and kind of get it out there, see if it gets a little traction. And so knowing how these mechanisms work on the inside and looking at how we're using them, there's a lot of, well, it's inefficient the way we're using it. So when I start thinking about how I look at the disk structures on the disk, and I have been a kernel hacker on ZFS. I've got several things I've lended for ZFS. I've worked on EXT and a whole bunch of other things. And for a guy who's designing a file system, I've even written a UDF implementation from scratch. When it comes time to write a file system, you try to find structures. You know, the old C coders paradigm that if you get your data structures right, the rest of the program writes itself. Well, every successful file system starts with a set of data structures that can map the user's data, because most of us that here in this room, the only thing we see is the result of fopen in some stream. Sometimes we care about ACLs or POSIX adders or whatnot. But there's a whole bunch of stuff that goes on behind the scenes that makes that look kind of seamless. So I started looking at what we're actually dealing with and the native structures of Filecoin sectors and partitions and all those other things. Good golly, that they lend themselves to something that starts smelling and looking like a file system all unto itself. And so we got 32 gig sectors, 73 tibs of a 73 tib partition of 2,349 sectors. And when it comes time to do the proof data, we're reading 16K random offsets per 32 gig sector. And that's the hardest part of this whole thing. All of the proof data is only 160K. All of the other proof data for an entire Filecoin partition is 384 megs. But you take any non-trivial file system and you start scaling it up to the PB range, and all of a sudden that becomes a hell of a job when you're just trying to pull out the little tiny taste test across that many disks, that many platters, all organized and put together through metadata. And so I got to thinking about this in, let's see, yeah, a single stripe of data, when you're doing any kind of clustered file system, a single stripe is chunked across multiple hard drives. So we're talking about trying to do that 16K read. We have to find out which hard drives are storing that data, have all of them do a random read because they're doing it out of order now, which means that I can't reconstruct that stripe of data that I've got distributed across my array. If I've got it spread 8 ways in a classic system, I can't reconstruct that stripe of data until the slowest guy returns his element there. Now, that, if I've only got one thread that's accessing this stuff and everything's under ideal conditions, it works pretty good. Where things start getting crazy is if I have multiple accessors, or God forbid, if I'm doing writes at the same time, to reconstruct that one shard or that one stripe of data that's distributed across all these different hard drives. To get to that one point, I have to do a whole bunch of metadata lookups to get to that point where I'm retrieving that one little chunk of data. And I'll try to speed this up here. This is a very entry-level overview of what happens on an ext4 file system before, and this is single spindle, single disk, nothing complicated. These are all the structures you're navigating to get down to an extent in the ext4 file system. This is the data that when you do an fopen, this is the thing you care about. This is all the stuff it takes to get there. And this is not, ext is simple because it's single disk, single volume, whatnot, and we've overlaid on that. This is what it looks like for ZFS. So we've got these top level D node structures. There's an Uber block, and the Uber block maps the D nodes. The D nodes map to SPAs, and there's metadata slabs and all that good stuff. But it all comes down, trickling down through here. All this is happening on every participating disk in any particular VDEV, and each ZFS file system is made up of one to n multiple VDEVs. All these lookups, all these indirections, and by my benchmarks, under the ideal circumstances, to read one 4K block or 16K block from ZFS, it requires between 4 and 6 metadata lookups, usually smaller than the one you're after, to get to that one block. Which is why your random read performance on these bigger clustered file systems tend to absolutely blow chunks. You got all this stuff going on, but I look at Filecoin and it's like, oh my God, this is damn near a file system all unto itself. What I did for a couple of experiments is assuming 32 gig sectors, beautiful, fixed size chunks of data, arranged in Filecoin partition, 2,349 sectors per partition. Beautiful, beautiful. And so what I started doing is I just played with the stupidest, simplest thing that could possibly work. Take these huge defect-free volumes, and I don't care if it's a ZVol coming from ZFS, if it's a Core Vault hardware RAID type volume coming out of a vendor's storage subsystem. I don't care if it's an MD RAID or an LVM volume. Anybody in here ever work with a virtual machine in any way? Probably everybody has. What's the first thing they do is they create some kind of VHD file or some kind of linear file to simplify that as much as possible, because you're going to be imposing some other structure on top of it. Only in the case of a Docker and a Union FS do you pull in host level file systems. Why? Because it adds no value. It slows you down. And there's a reason why all the virtualization guys go to some kind of SAN type concept eventually, because all they want is that block storage. They want that linear block storage because you can't do the small operations fast on anything else. When I took this system here and I took these, 8 petabyte volumes, and I started slicing them up into GPT partitioning, supports up to 120 slices within any given disk volume. And I started looking at the geometry of Filecoin and the layout of the sectors, the 73 TIBs per Filecoin partition. I can create all these labeled GPT volumes within a single GPT partition or a GPT volume. I can create the labeled GPT partitions inside of a single GPT volume, and I can create multiple of those. What's more is I can label those top level volumes and the partition labeling so that they have a deterministic name, something that identifies a Filecoin partition and a map of start and end sectors in that partition. Okay, that's cool. I got these huge linear block arrays, but something else starts happening. All of that descriptive data, that metadata that we used to have to crawl disk structures for, now it lives in SysFS in RAM structures that never have to be updated. It's instant. What's more is because I have created these logical mappings that have deterministic ranges in the disk structure underneath of it, I can't ever have a fragmented file system. The LBA 0 of a certain slice of a certain partition is always going to hit the same number of disks exactly the same way. It's never going to change. Anybody who's ever had to do a defrag operation or whatnot, or even in the case of ZFS, which doesn't support a defrag operation, after a little bit of while, things become completely screwed up because the allocator doesn't know who's on first and who's on second when it comes time to start allocating. In the case of ZFS, the SPA allocators have no idea what the relationship is between things. We get to drive that home if we do something like this. So what I'm thinking is that if there's only, I haven't studied it fully since we went with the split storage model, but at about that time, there was only 2 Go modules that I could find that actually did the fopen, did the seek, did the read, did the close, and returned a taste test of random offset data involved in a proof worker. And so I said, I started thinking to myself, we got this beautiful structure, how can I make this super fast? And at the end of the day, that function in Lotus, all he was doing was returning a byte array. Huh, I know how to do that. Memmap functions. So instead of going through the complication of opening a file system, getting to my metadata, finding a named directory path, finding its offset on the disk, challenging the subsystem to go out, find that offset, do a read, page fault that into my user process, and have that magically show up in my byte array, go straight to the punchline. I find out which sector I'm in, or which partition I'm in, which sector I'm in, what the offset is, memmap function, nothing's happened yet, nothing's happened yet. Memmap that 4K or 16K range in. My user mode process does an index access of byte 0 in that array. Bang, the virtual memory subsystem does what all that other stuff would have done, and that whole 4K page pulls in, or 16K page, or whatever it is. So I've skipped everything else, and I went straight to the punchline of what I want. I want that little bit of data that's out there, and I've been able to skip all the metadata lookups it gets to get to there. What's that?
Amazing.
What?
I just said, dude, that's like, this is big.
Let's see. So this sounds really complicated, right? Everything I've been talking about? This is literally the two-line batch script that set up the GPT partitions with a Filecoin partition identifier, what I was calling a zone, and a sequence string, which happened to correlate to which range of sectors we had in there. This is it. This is my provisioner for these volumes. And again, it works against ZFS-Z volumes, works against LVM volumes, doesn't make any difference. MD RAID, all works the same. Or in the case of like a Core Vault or some of the higher end SAN solutions, once I have these GPT partitions, and GPT is one of the N things that I could do this with, but literally that's how I create this decorated namespace in SysFS, so I know where to do my memmap range, and I'm done. So I just deployed a system that had 336 drives on it. In fact, I can pull it up here in a little bit. But 336 drives arranged in, I forget how many VDEVs. But the punchline is, over the course of about several days of playing around, I was able to take one of our reference implementations that we use also often. Typically in Filecoin, we use a pair of big JBODs and a pizza box server, and we come up with some kind of RAID Z2, whatnot. So I was able to double the performance of that thing and have the compute with just a couple of days of playing around and with CFS. So now it's a 4-PIB array that performs twice as fast. But the caveat here is no matter how much tweaking I do to that, I can't ever get the 4K random read data rate above about 1 megabyte per second. Can't be done with it almost cannot be done with a conventional HDD, large capacity disk array, simply because each one of those reads, each one of those 16K IOPS requires 4 to 5 metadata lookups, each of them small 4K or 16K lookups, the reconstruction of a 8-way stripe or bigger stripe, and the latency of the slowest contributing member of that stripe will dictate when I'm finally I/O complete on that, and I can do my page fault and hand it back to the user mode process. Just doing I did a simulation here, 4K random read against 1,800 virtual Filecoin sectors in a partition, and I made it across, created across 24 volumes and just 6 storage structures. So at the end of the day, it looked like 144 volumes because of the way I had sliced everything all up. But this same thing that could not achieve more than 1 megabyte per second random read performance, 180, 155, 196, 218 megabytes per second with a corresponding collapse in the latency involved to get there. And the compute required to do this, of course I'm not computing all these other things that I have to do with the file system. I'm not having to do anything else except in the user mode application, do a memmap range to a fixed offset calculated inside of a GPT slice that happens to be part of a named logical volume. Boom, done. And if we decide to take this on, I think there's some huge efficiency improvements. And I just threw this in here at the end. These are all the tunables and whatnot that Alan Jude and I came up with for tweaking the shit out of ZFS. This is how I was able to take that standard reference implementation and 2x it in almost every dimension, including reducing the compute required by a factor of 2. So this is, you'll see this all these change commits in OpenZFS 2.2 when it finally lands. Questions? Good. That's it.
What does this specifically mean for the storage provider?
What's that?
What does this specifically mean for the storage providers and window posts or winning posts?
So, in the context, one of the things that I found a lot of fun to do at Seagate that would be very expensive for mere mortals to do is to see how big of because your return on investment. There's a combination of compute and storage, and you want to run that convergence line so you're maximizing everything for a given level of performance. There's an upper ceiling to how big you can create a storage array and still have it survive both Windows and winning post. That ceiling on HDD, we're about at that right now on JBOD at 336 drives. We've got about 20% margin by my calculations. There's reasons why I can't go any higher than that. And but if I can go bigger than that, then as my economies of scale work out, I have reduced compute, have reduced resources. This mem mapping against volume ranges, I need no compute whatsoever for that. I mean, that's dead nuts simple. And so all the other stuff that would be going on, so I've now reduced myself to maybe a core or half a core of some compute function. I've reduced the compute from, on the 336 drive solution, I'm keeping 24 cores busy about 50% of the time. The thing that I presented here would need half of a core and no additional memory whatsoever. And it would probably scale to the net level of 900 to 1,500 disk drives if you can get the interconnects to work. So all the economies of scale start shifting in that. Where this gets really, really interesting is if you use something like a core vault technology, which I was an architectural engineer on at Seagate, that turns a JBOD into something like a ZFSD RAID 2 array where all the smarts are implemented in ASIC. So today, a classic 5U84 JBOD from Seagate costs around $34,000, $35,000, gives you 80 drives. The 2.5 petabyte core vault gives you two logical volumes, about 1.5 PIBs each. The box itself is presenting about 2.5 petabytes, and it sells for less than what one 5U84 does. The problem is you have to integrate a whole bunch of those to make into a file system because there's only one or two targets. I did those experiments against the slowest enclosure that I knew of, the core vault, and I was still blowing away JBOD on any file system I know of. So that means it becomes infinitely practical at this point for me to have a stack of these $32,000 fully populated 2.5 PIB JBODs, core vaults. And if I can use this mem mapping volume slicer, I can still have I can have better I/O performance, random I/O performance than I would ever get out of half that size capacity on JBOD, be more performant, less compute, and more cost efficient by almost 20 to 30% over anything JBOD.
Thanks.
Is this? Yeah. I am so jealous suddenly that Filecoin has 32 gigabyte sectors. Like, holy cow! This is a major point of feature differentiation with Filecoin to have 32 gigabyte sectors if you can map the partition table directly. Like that's
Yeah. That's
an
exactly what I'm
incredible. Right, that's what you're doing. You're just mapping partitions directly. Oh my gosh! Of course, this is a huge performance
I
differential.
can all of a sudden start monetizing Chia-like commodity deployments for Filecoin.
I suddenly want to make every distributed system use this technique, and I don't know how, but like Filecoin is clearly well suited for it. Very
well, we still have to. There's only two Go modules. There's only two Go modules in the Lotus framework that I know of that have to change to accommodate this. And the interface doesn't have to change. The interface stays constant. The Go interface. All we need is another module on the side over there to side load this thing, and we're done.
What are you doing with this idea? Where's it going? Where's its home?
I'm selling it. So it's really one of these days when I have a little bit of free time, I'll go off and do it. I went through and built the prototypes. Super stretch. This is where it gets really interesting. So, well, we don't need to look at it anyway. I'm working on a project because I was an architectural engineer on the Core Vault technology. I know how to do Core Vault better than Core Vault, and I also know that the upcoming, whether the MAMR drives or the HAMR drives, what's critical to these hard drives that are going 30 terabyte plus is that typically they have 20 surfaces, 10 platters, 20 surfaces, 20 heads, and the probability of one of those surfaces going bad over the 5-year lifetime of the drive is pretty high. It's a pissing shame that you throw away a 30 terabyte drive and suffer all of the rebuild and rebalancing and regeneration, resilvering, whatever you want to call it, all because 5% of a disk surface went offline. The prototypes I gave back to Seagate, and I'm now pitching back to WD, leverages the concept of block zone devices. And WD did a whole lot of work to support SMR drives, to where block zone devices have different recording characteristics across the entire surface. My idea is to use block zone devices to map a range of CMR zones on a linear address space of a conventional hard drive, such that a file system such as Bcachefs, which is going in Linux 6.6 this time around, Yahoo! Bcachefs, thanks to WD, knows how to do SMR, CMR block zone mappings all damn day long. If I can get the drive to report where the failed domains are going to be on the drive, yes, light goes on, then I can design my erasure coding and never, ever replace a disk drive, ever. If I design my erasure coding, never do a rebalance, never do a regen. And the ideas that Seagate has right now, they're leveraging over provisioning and stupid trim commands. It'll never work at scale. They're just trying to please Microsoft and Google because that's what they know how to do. Related to this, I'm developing an immersion cooling thing. I really don't care about the immersion cooling thing, except for the way that we can start deploying storage servers in people's barns and closets and garages, because I don't have to have the environmental footprint. And at the same time, we've got a confluence of these NUC class compute devices that are getting super, super cheap. The one thing that's missing from all these NUCs is a by 16 PCI 3, even a PCI 3 expansion card. Because what's come online in the past 6 to 12 months is native 24-port SATA adapter cards, but I have to put them on an X16 interface. However, the form factor for both the SBC and the PCI to SATA bridge, and it's not a multiplexer, this is, honest to God, 24 real ports of SATA, both of those can fit in a 4x6 or a 4x5 form factor that mirror about the same physical footprint of a single 3.5-inch drive. So I can come up with a disk module, throw some Thunderbolt or 10 gig networking on the back on one of these commodity NUCs, 24 ports of SATA, plumb in a bunch of these 30 terabyte HAMR drives, leverage Bcachefs against the drive level, and tie them all together under a D-RAID type topology and achieve something that's got better performance than the Seagate Core Vault technology in a replaceable line module of 24 drives at 30 terabyte. And then I bring those blocks out, and I start doing something clever like direct mapping of my Filecoin file system, my Filecoin SAN file system, onto an array of those, where 5 of them on the shelf. Now I've got over 3.5 PIBs, relatively defect-free, almost zero maintenance drives. So anyway, and then we take it to the next level. Well, I know what happens next. I got some ideas there too.